Okay, so we're going to do lesson 7, nonlinear relations and their intercepts. Introduce mapping diagrams and ordered pairs as representations of relations. Review dependent, independent variables and continuous discrete inputs and outputs. Determine the linearity of an equation from a table of values, graph, or equation. Okay, that was repeated, but that's okay. Then we're going to determine the x and y intercepts, including where multiple exists for quadratics. Okay. So, linear and non-linear relations. A relation can be described using, let me get a pen going. Can be described using words, a table of values, a set of ordered pairs, a graph, a mapping diagram, or an equation. We're going to discuss what a mapping diagram is in just a second. So, fill in the blanks to complete each representation of this relation. In words, the cost of parking in a particular lot is $2. To park here once, it costs $2. Twice, it costs $4. 5 times, it's going to cost $10. Let's fill in the table of values. So we've got the number of times parked, which is N, the cost, which is C. If we park one time, it costs, what just happened? Okay, when we park one time, the cost is $2. If we park 2 times, the cost is $4. If we park 5 times, the cost is $10. Okay, number 3, let's write this as a set of ordered pairs. 1, 2, 2, 4, 5, and 10. And if we do it as a graph, we're going to have, if we don't park at all, it's 0, 0. If we park one time, it's $2. If we park 2 times, it's $4. If we park 5 times, it is $10. Now, let's take a look at question number 5. A mapping diagram shows us what the relationship is between variables. So our variables are N for the number of times that we park in a lot, and C is the cost. So when we park one time, the cost is 2. So N maps directly to C. If we park 2 times, it is 4. If we park 5 times, it is 10. Okay? 5 only maps to 10. It cannot map to 4, and it cannot map to 2. It wouldn't make sense. The equation that represents this relation is, okay, so let's take a look. What is our slope? So I've got C is equal to, now our slope is 2. So it's going to be 2n. What is our y-intercept? Well, our y-intercept is 0. So it's just going to be C equals 2n. In this scenario, the independent variable is the number of times parked. The cost depends on the number of times we park. So the dependent variable is going to be the cost. The input values are going to be N. The output values are the cost. Is the data discrete or continuous? Well, here it wouldn't make much sense if we joined the points because we are parking 1 time or 2 times or 3 times. We can't park 2.5 times, okay? So in this case, it is going to be discrete. Is the relation linear? Well, take a look. Does it form a straight line? Yes, it does. So, yes. Okay, next page. Determine if a relation is linear. From a graph, a relation is linear if the points form a straight line. Keeps moving around on me. From a table of values, a set of ordered pairs, or a mapping diagram, a relation is linear if the slope between any 2 points is the same. All points are collinear. There's also another way to tell us if something is linear, if it goes up by a consistent value. Okay, and I'll show you that a little later on. From an equation, the equation must be able to be written in the form y equals mx plus b, where both the degree of x and y are 1. So notice that the exponent on the x is 1. The exponent on the y is 1. So if the exponent is 1, if the exponent on x is 1, then the relationship is linear. And I'm also going to highlight that. All right. From a word or a scenario, there must be a constant rate of change. So going back to the parking question, the rate of change was 2, and it's 2 all the time. All right, from a graph, it's pretty easy to see if something is linear or not. So it says, determine whether each relation is linear. Where possible, write a linear equation for the graph. So is this one linear? No, because it's a curve, so it is non-linear. Is this one linear? It sure looks like a straight line, so this is linear. And we should be able to come up with an equation. There is no y-intercept. All of the points have an x value that is -2. Therefore, our equation is x equals -2. This one is linear because it is a straight line. The equation is going to be y equals, what is our slope? Our slope is +1, so it's going to be x, and our y-intercept is -5, so x minus 5. This one is definitely non-linear. Okay. Determine whether each relation is linear. If linear, write the equation relating the two variables. Okay, so the way that we can tell that something is linear given a set of points. Let's think about this. I have my values for x and I have values for y. I'm going to put them in a table. So when x is -2, my y value is +5. When my x is 0, my y value is 8. Here it's going up by 2 and this is 11. Now think about this for just a second. Are our values going up by a consistent amount? So here I'm going up by 2. Okay, so that's consistent. What about this one? I'm going up by 3 and by 3. So yes, this one is definitely linear. And then it wants us to write an equation relating the two variables if it is linear. Okay, so what I need to know is, what is the slope, first of all, for this line? So let's find the slope. M equals, so I'm going to take my y2, take away y1, so I'm going to go 8, take away 5. And here I'm going to go 0, take away -5. 2. So m is equal to 3 over 2. Now it gives us our y-intercept. Our y-intercept is always where x is equal to 0. So that's my y-intercept. So my equation is going to be y equals 3 over 2x plus 8. Okay, let's try this one. So, is it going up by a consistent amount? So if I go here, it's going up 1. Here, it's going up by 8. Here, I'm going up by 3. But here, I'm going down by 8. So this is non-linear. Okay, for the next one, I am going up by a consistent amount here, so plus 1, but here I am going up by 5, and here I am going up by 7. So this is non-linear. Okay? All right, let's try this one here. So I've got a mapping diagram. So what I'm going to do is I'm going to write out the coordinates. So take a look. I've got 1 maps to -2. Here I've got 3 mapping to -6. Here I'm going from 4 to -2. Okay, now take a look, something interesting right here. I've got 1 mapping to -2 and I have 4 mapping to -2. So we can check the slope, okay, of the 3 points, seeing if they're collinear, but what we can also do is just sketch out a graph. It doesn't have to be perfect. There's more than one way to do these. So if I have 1 and -2, 3 and -6, so 1, 2, 3, 4, 5. So let's say it's going to be down here. And then I have 4 at -2 again. Well, that doesn't look linear to me because it follows this pattern. Okay, so this is going to be non-linear. Okay. So here, now we're going to take a look at determine whether each relation is linear. Now what I'm going to do is I'm going to pause really quick and I'm going to pull up my graphing calculator because I'm going to graph these for you so you can see what they look like, okay? Okay. So, for most of these, we should be able to figure out whether or not they are linear or not. Remember that for it to be linear, the exponent on x must be 1 for the relation to be linear. Okay, so looking at the very first one, y equals 2x minus 8. Well, that just is y equals mx plus b. I'm going to change the color of my pen. Therefore, it is linear. Okay, for the second one, okay, I can totally rearrange this and it's going to be y equals mx plus b, but looking at my variable x, the exponent is 1. Therefore, this is linear. Now, y equals x squared minus 1. Looking at this one, the exponent is 2. Therefore, this is non-linear. And it is actually quadratic. And I'll show you what that looks like. So if I pull up my calculator, maybe, and I turn it on, maybe, there we go. Okay, y equals, I'm going to clear my graphs here. Okay, gives me x squared minus 1. And that's what my graph is going to look like. Now, looking at this one, I've got y equals 1 over 4x. The exponent on this one is 1. Therefore, this is linear. Look at e, y equals 4x to the power of 3 plus 1. Well, the exponent on the x is 3, so it is non-linear. Okay, let's see what that one looks like. So going back into y equals, I'm going to clear that, and I get 4x to the power of 3 plus 1. Okay, gives me kind of a squiggle. Okay, so it's definitely nonlinear. What about this one? Y equals 1 over x. Well, it looks like the exponent on the x is a negative. But what we actually have is positive 1. But what we actually have is y equals x to the power of negative 1. Okay, and I'll prove it to you. I'm going to graph it. Okay, so I've got 1 divided by x. Graph. Okay, so I get something that looks like this. So it looks like that. Okay. I can't draw to save my life, so bear with me. Now, let's see what happens if I delete that graph and do x to the power of negative 1. I get the exact same thing. Okay, so this is definitely nonlinear. Okay, now I've got y squared plus 3 equals x squared minus 8. Looking at the x squared, okay, I have an exponent of 2, so this is definitely nonlinear. But this is an interesting graph. If I rearrange this, so I go y squared equals x squared minus 8, take away 3 gives me negative 11. And then I square root both sides to get y by itself. I'm going to get y equals the square root of x squared minus 11. Now let's see what happens when I graph this one. This is an interesting one. Y equals, I'm going to clear that, and I get the square root in brackets x squared minus 11. I get something that looks like this. Okay, so that is definitely nonlinear. Okay, the next one, y equals x over 7 minus 1. Well, this is just y equals mx plus b, and I can rewrite this as y equals 1 over 7x minus 1. So this one is definitely linear. I'm going to erase this. This one is linear. Okay, y equals 4. So this one we should recognize as a horizontal line. So this one is linear. Okay, passing through y is equal to 4. So our graph is going to look like this. So where y is equal to 4, I've got a straight line. Okay? All right, so now you're going to work on the check your understanding of 7A, and then I'll come back with you with part 2.